Hi everyone and welcome back. Today we are stepping into one of the most important ideas in all of machine learning, something called the cost function. You can think of cost function as the model's scorecard. It is basically telling us how well our linear regression model is doing and how far we are from where we want the model to be. Let's take this step by step, but before that, let us go through a quick recap together. We have a training set made of X, which is the car's mileage, and Y, that is the car's actual or true selling price. We decided that our model is a simple straight line with the equation W dot X plus B, where W controls the tilt of the line and B decides where the line crosses the vertical axis. The two very important numbers, W and B, are called the parameters of the model. During training, we're going to adjust them until our line fits the data as nicely as possible. Now let's visualize how W and B affect the line. To build the intuition how the slope and intercept together shape the model, let us look at a few lines drawn using different values of W and B. You can see that when W equals 0, the line becomes perfectly flat. Basically, that means mileage doesn't matter at all here. And when B changes, the whole line slides up or down because we said B decides where our line intercepts with the vertical axis. Notice that a bigger W makes the line steeper. But what is our goal here? Our goal here is to make predictions as close as possible to reality. Here's the problem we're trying to solve. For each training example, a prediction Y hat should be close to the real price Y. But how do we measure close? Let's look at an example from our data set. On the slide, you can see the training data as blue crosses and the best fit as a red line. The question now becomes, how do we mathematically decide whether this red line fits well or if it's doing a terrible job? That's where the cost function comes in. And that's where we need a way to measure error. For each training car, we have the true price, which is Y, and the predicted price, which is Y hat. Naturally, the error is the difference between the two, or Y hat minus Y. If the model predicted too high, that means the error is positive, which is Y hat is bigger than Y. If the model predicted too low, that means the error is negative, which means Y hat is smaller than Y. To avoid positive and negative errors canceling out each other, we need to square the error. So our error becomes Y hat minus Y squared. That always gives us a positive number. This makes all errors positive and makes big mistakes hurt even more, which is exactly what we want. Now, let us visualize the squared error. Each red dot on our slide indicates how big the squared error is for one training example. Our visualization shows that points far above or below the model produce a tall red bar and points close to the line produce a short red bar. Naturally, our objective here is to reduce the error to the smallest value possible. Let's see how we can use the individual errors to measure the cost function and decide how good or bad our model is. To do that, once we compute the squared error for every example, we need to sum them all. Summing alone would make the cost grow just because the data set is large. So we compute the average squared error. And by convention, we divide by 2 for reasons that become clear in our lesson covering the very interesting concept and important concept of gradient descent. That is our cost function. It tells us in a single number how bad our model currently is. The cost function is denoted by the letter J. A large J of W and B means a terrible model or a bad fit. Small j of W and B means a great model or a good fit. Now, why does this matter? Once we have a cost function, we can finally ask which W and B make the cost function as small as possible. That process, minimizing cost, is how the model learns. And that's exactly what we will explore in the next video. See you in the next lesson.